All right, good morning. This is College Algebra. It's March 19th. A couple of announcements to make here at the beginning as we head into exam 2. First of all, WebAssign homework. There was a WebAssign homework due yesterday. 5.4 was due yesterday. And I extended 5.5 and 5.6 to give you a couple days past spring break. So those were originally due yesterday on the 18th, but I've extended them, and so now they're due at the end of the day tomorrow on March the 20th. So you still have another day and a half or so on 5.5 and 5.6. The next ones that will be due will be 3.4 and 3.7. 3.4 is on composition, and 3.7 is on inverse functions. I originally had that set up to be due on March 25th, but that really didn't make any sense because that was in the middle of your testing window. That's material that's not even on exam 2. And so I changed the date on that. You know, I set up these dates at the beginning of the semester, and it made some significant changes from the fall semester. And there's a few places where things didn't make a lot of sense. 3.4 and 3.7 was one of them. So those are now due April the 2nd. Most of the time my homework is due on a Sunday. The April the 1st is Easter Sunday, so I decided just to go ahead and make those due on April the 2nd, on the Monday after Easter. And then, you know, after that, there's some assignments to pick up after that that are due like on the 8th of April and go from there. All right, exam 2, just a couple things about exam 2. The review has been posted on Google site now for, almost 2 weeks. So you've had a lot of time to be looking at the exam 2 review. Please let me know if you have questions about the review. I'll be happy to help you out with that. The window opens on March the 22nd and closes the 27th. So you have 5 days essentially to take the test. Like someone was just asking me a minute ago, the test, just like exam 1, is a paper and pencil test. You are not completing this on WebAssign or on a computer or anything like that. It's show all of your work. Make sure that you have a photo ID with you when you go and take the exam, wherever you're going to take it. I will put a time limit on the test, and usually what I do is I set it as a 2.5 hour time limit. That should be plenty of time to take the test. From what I saw on exam 1, most people finish that test in somewhere around an hour and a half, so you should have plenty of time to take the exam. Make sure that you show up at a testing center, whatever testing center you use, with at least 2.5 hours for them to be open after you start the test so that you have enough time to take the test. Office hours, where I'll be available to you for help. Tomorrow I'll be online from 11 to 12, and then again Sunday evening from 8:30 to 9:30. Note that usually on Tuesday evenings I'm online also, but tomorrow night I won't be. So those will be my online office hours this week: Tuesday 11 to 12, Sunday 8:30 to 9:30 in the evening. I will be on campus this week, Wednesday from 4 to 6 p.m. and Thursday from 9:30 to 11:30 a.m. The calendar may say 9 to 11, but on Thursday it'll be 9:30 to 11:30. Remember that my office is in Winship 115K at the North Harris campus, and I will actually probably move us to a slightly bigger room than my office. That's what I did last time. So, but go to Winship 115K, and there will be a note there to go around the corner. There's a bigger room that I'll use for my office hours. After today, my next lecture will not be posted until March 28th. So I'll resume lectures on the 28th of March. That's exactly what's on your calendar also. So we'll obviously take off this Wednesday because I'll be on campus, and then the following Monday because that's in the middle of the testing window. So next lecture will be the 28th, and we'll be starting exponential functions and logarithm functions when we come back after this exam window is over. So today what we are doing is we are kind of finishing up some material, some preliminary material that we need to discuss before we can talk about exponential and logarithm functions. And so what we've done is we've kind of gone back to chapter 3, and we're covering sections 3.4 and 3.7. those are things that we need to be able to talk about exponential and logarithm functions. So we're talking about composition, function composition in particular in section 3.4, and in section 3.7 we were talking about functions that are inverses. And so we are going to just finish talking about function composition today, and then we will get into talking about function inverses. So that's our first step today, is to talk about function composition, and then to kind of go from there now. So function composition, as far as notation goes, when you compose two functions, you'll frequently see that operation symbol. You'll see an open circle between two functions. It says that you're composing those two functions. You can read that f circled g if you want, or you can read it f composed with g. Either way is okay. And the definition is that this is f of g of x. It's the f function of the g function. And if you do g composed with f of x, g circle f of x, then that would be g of f of x. Notice that the functions, the actual letters you use for the names of the functions, are actually written in the same order, so that should help you kind of keep it straight between the two functions. All right, and if you could extend this, if you're composing, you can compose a function with itself. So for example, g circled g of x would just be g of g, right? Or f composed with f would be f of f, etc. You could compose them any way you want like that, right? It's always the first function of the second function, though, is what we're talking about. All right, so if we have as an example here, f of x equals 2x minus 1, and g of x is equal to x squared plus 4, like that, then let's look at some examples here that we want to be able to talk about. So let's say, for example, we talk about f circled g of 2. So f circled g of 2, and we hadn't really gotten into this kind of problem specifically last time. But you would write down the definition. This would be the f function of the g function of 2. This is f of g of 2. Right, and this is saying operate with g first on 2, and then f takes over after that. I'm going to draw a picture of how this works in a minute. So the first thing you do is you calculate g of 2. Right, and so I'm going to put that underneath in a different color here. G of 2, you just go to the g function, right? That's 2 squared plus 4. Right, every place you see an x, you put a 2. And that would be 4 plus 4, or 8. Right, so g of 2 is equal to 8. And so we go up to our little calculation, our function calculation here, and this would be f of 8. Right, notice that 8 gets put in place of g of 2 right there. G of 2 and 8 mean the same thing. I'm going to highlight that right here. There's g of 2 right there. There's 8. And based on this calculation right here, g of 2 and 8 are interchangeable. They mean the same thing. And so that's what I'm doing, is I'm just replacing g of 2 with what it's equal to. And then this says go to the f function and replace x with 8. So this would be 2 times 8 minus 1, which would be 16 minus 1, or 15. All right, so now with a picture of what's going on here, you're starting with, I'm going to draw a circle like this, a big circle. You're starting with the number 2. Right, there's the number 2. And the first function that operates on 2 is g. And so g takes 2 and takes over like this. So here's g right here, and we're calculating g of 2. And that's what that dot is right there. G of 2 is equal to 8. This is the domain of g right here. Right, the domain of g is what you would start with, the x values that g operates with, because f of g of 2, the first function that operates there, is the function g. And then what happens after that? Then f takes over, and f takes 8 like this, and f takes 8 to 15. And so that's kind of one way to draw the picture. Now, the transition between the two, that middle circle, notice that has to be the range of G, but also the domain of F, right? It's where G lands, and it's where F starts out. And so it's the output values for G, but it's the input values for F. And so there is an issue there in that do they fit together correctly? You know, do the output values for G or do they equal the input values for F? And in many cases, that's not necessarily the case, where those two align. And so you have to be careful there to make sure that those functions align with each other. And that, you know, that can sometimes be a problem. Now, we're not going to make a big deal about that at this point. We're not going to try to fit the two functions together and make sure we've got the correct range for G so that the domain for F fits in right. We're going to kind of assume that that works out correctly. If there are any restrictions, we'll just base it on the function that we have at the end. But we're not going to make too big a deal about the way that works out. But I did want to kind of talk about that a little bit with pictures about how those have to line up. So these are the output values for G right here. So I'll say output for G, in other words, the range of G. But it's the input values for F, in other words, the domain of F. And so you have to be a little bit careful about that transition when you're looking at composition. Like I said, we're not going to make a big deal about that at this point. All right, and then finally, you know, so that, I'm going to put a bracket there. That's what we're talking about with that circle right there. All right, now that picture, I think, is going to be a good picture for us as we transition into talking about inverse functions. That's one reason why I like to talk about pictures like this, is because it's to be a good lead-in to talking about inverses. It also emphasizes the fact that we are not operating with both F and G at the same time. That when you're looking at composition, you're first operating with one function, and then you're operating with the other function afterwards. Okay? So let's look at another example. Let's look at G circle F, or G composed with F of -1. G composed with F of -1. So by definition, that would be G of F of -1. And just like we did on the last problem, the first calculation we would make here would be F of -1. Right? That's the inside piece there. We need to figure out what F of -1 is. So we go to the F function, right? And wherever we see an x, we substitute -1. So that gives us -2 minus 1, or -3. So F of -1 is equal to -3. And so what do I do here? I take my function statement here, and I replace F of -1 with -3. Right? And again, let me highlight that. We're saying here that F of -1 and -3 are the same thing. And here's the calculation that shows that right here. Right, and so now my function notation is simply find G of -3. So now I go to the G function, and in place of x, I substitute -3. So you have 9 plus 4, and you get 13. All right, and so the picture that I just drew a minute ago kind of fit in a similar picture down here. The x value we started with was -1. And the function that started operating on -1 first was f, right? And we were looking at what f did to -1, and f took -1 to -3. And then G takes over. So notice in this composition, the functions are operating in the reverse order than they did in the first one. So G takes over with -3, and G takes -3 to 13, like that. All right, and so again, we're talking about F operating first, and then G taking that answer and applying it to that answer, like that. All right, so now let's continue to talk about those two functions. So you have F of x is 2x minus 1, and G of x was x squared. That was x squared plus 4, right? X squared plus 4. So we were looking at, looking at some composition functions at specific values. So now let's actually create the function. So let's look at f circle g, or f composed with g of x. So f of g of x would be, by definition, f of g of x. And so I start with that inside function again, g of x. There's no calculation to do here, like we had no numerical calculation like we saw on the previous two examples. But instead, what does g of x do? G of x goes to x squared plus 4. So we still evaluate g of x, but we write down the definition here. And so what am I doing here? I'm saying that g of x and x squared plus 4 are the same function there. And then this says go to the f function, and every place you see an x, you put x squared plus 4. So I put the x squared plus 4 function into the 2x minus 1 function. I would use parentheses here, definitely use parentheses. And notice what I did is I took my f function, and every place I saw an x, I put an open set of parentheses like that. And I'm dropping the x squared plus 4 function into that function. You're literally substituting the g function into the f function here. And then you just simplify that expression algebraically. So you have 2x squared plus 8 minus 1, or 2x squared plus 7. And so that would be our function for f circle g, or f composed with g of x. You could draw the picture just like I was doing a second ago. You could do exactly the same thing that we were doing a second ago. Right, so what do? We started off with x in this case. And what function operated on x first was g. Right, and what does g do to x? G takes x, and it takes it to g of x. So it takes it to x squared plus 4. Right, takes it to g of x. And then what happens? Then f takes over. F takes over and takes x squared plus 4 to 2x squared plus 7. Like that, right? And that is the definition for the composition function. And notice the composition function, in some ways, is a kind of skips over the middleman here, doesn't it? You've got f circle g of x is defined to be 2x squared plus 7, like this. That look a little bit better here. All right, so if you were going to make a calculation here, so like let's say I was going to do f composed with g of 6. F composed with g of 6. Well, you now have two ways to evaluate that. One way would be the way we were talking about in the previous screen, or the way the pictures are drawn out here, where you operate with one function and then the other function. So this would be f of g of 6, like that. And then you'd evaluate g of 6, right? G of 6 here is 6 squared plus 4, or 36 plus 4, or 40. So this would be f of 40, like that. And then you'd go to the function f, and you'd evaluate that at 40. So you'd have 2 times 40 minus 1, or 80 minus 1, or 79. Right? So f circle g of 6, or f composed with g of 6, would be equal to 79. Or the other way you could do the same problem is you could now just use the function that we've created above. So f composed with g of 6 would be equal to 2 times 6 squared plus 7. So what are we doing here? We're using the fact that f composed with g of x is 2x squared plus 7, right? Which was the function that we created up at the top of the screen there. And so notice what happens there. You get 2 times 36 plus 7. Sure enough, you get 72 plus 7, or 79. You obviously get the same thing. So you can evaluate that function value either way. first operating with one function and then the other, or create the composition function first, and then, here's the composition function, and then just evaluate that composition function at the numerical value that you're looking at in the problem. So that would be two different ways to do kind of the same thing there. All right, let's look at maybe problems that are a little bit more involved as far as composition goes, so that you just see some of the algebra that kind of works out with some of these problems. They're not all going to be quite as straightforward maybe as you might think. So I'm in section 3.4 of your textbook. This is on page 218 of your book. And this is problem number 12. Number 12, you have f of x is x squared plus 1. And g of x is the square root of x plus 2. Oops. G of x is the square root of x plus 2. So the definition, or the directions rather, say to find f of g and g of f. Now the directions go like this. In the book, the directions say find f of g of x. Well, remember, that's the same thing as f circle g of x. So you'll see it written both ways. In WebAssign, you'll see it written both ways. So make sure that you know that f of g of x and f circle g of x mean exactly the same thing. And the directions also say find g of f of x. And so that would be obviously g circle f, or g composed with f of x, like that. All right, so they're asking us to look at both composition functions. Okay, so let's do the first one. So f circle g of x is f of g of x. And so this would say go to the function g and evaluate that first, right? So this would be the square root of x plus 2. Right, so in place of g, I put the square root of x plus 2. And then this says go to the function f. And wherever you see an x, you're going to put the square root of x plus 2. So the function f would be x, would be x squared plus 1. So I'm going to put that lightly right above, x squared plus 1. So in place of x, I put parentheses, and I've got the square root of x plus 2, like that. And then plus 1. Now you do have to make an assumption here, and it is an okay assumption to make. You've got the square root of x plus 2 squared, and that's only equal to x plus 2. You're taking the square root of something and then square it. That's only equal to the number underneath the radical as long as the x plus 2 you can be guaranteed is positive. But see, that's got to be true here. And when you write g of x equals the square root of x plus 2, we've talked about this before a while back this semester, but the domain of that function are only x values where x plus 2 is positive, right? So x plus 2 has got to be positive just based on that function right there, right? We don't have negative numbers underneath a radical because then you've got imaginary range values, which we don't want. In college algebra, we're only looking at real functions here, real valued functions. So we can, the bottom line is we can assume x plus 2 is positive, and because x plus 2 is positive, then this would be true here, that the square root of x plus 2 squared would be x plus 2. The only reason we can write that again is because of that statement right there, that this x plus 2 has got to be positive right there. And so we end up with the function x plus 3. And so that's our composition here, is f composed with g of x has got to be equal to x plus 3. All right? And then the other composition function would be g composed with f. And so that would be g of f of x. And so that would be g of x squared plus 1. And so that would tell us go to the function g, and so here's our function g. Wherever there's an x, though, what am I going to do? I'm going to put an open set of parentheses. There's my function g. And in place of the parentheses, or inside the parentheses, I'm going to put x squared plus 1, right? In other words, the x squared plus 1 function gets put into the square root of x plus 2 function here. All right, and then, you know, the parentheses underneath the radical really aren't necessary, and so you end up with the square root of x squared plus 3, and that would be the composition there. We cannot simplify that algebraically, and so that would be the definition right there. So here's our two functions, like that. Now, this is a good example of the fact that you know, the functions that you end up with may not look at all like the original function. Certainly, when you compose them, different things can happen as you compose functions like this. All right, let's look at problem number 14. I want to work a couple of examples here so that you've got some examples worked out in your notes. So that when you tackle WebAssign homework on this, you've got some things to look back at. So f is the absolute value of x, and g is 5x plus 1. This one, actually, when you look at the compositions here, this is not so hard here at all. This is not as difficult as the first problem. If you've got f circle g of x, that would be f of g of x. And so that would be f of 5x plus 1, right? In place of g of x, I put 5x plus 1. And now this says go to the f function, and wherever I see an x, I put 5x plus 1. And see, all you got to do here is just write absolute value. Instead of absolute value of x, it's going to be the absolute value of 5x plus 1. And that would be it. There wouldn't be anything you could do to simplify that. And so you'd be stuck with it as an absolute value like that. Just the absolute value of 5x plus 1. Not a big deal there at all. And if you operate the other direction, if you do g composed with f of x, this is g of f of x. And so this is g of the absolute value of x, like that. Right in place of f, I put the absolute value of x. And then I go to the function g, and wherever there's an x, I just plug in absolute value of x instead. So this is 5, instead of writing 5x, right, I've got 5 times open set of parentheses plus 1, and then in place of that is the absolute value of x. And there's really not anything you can do with that. I don't even need the grouping symbol there at all. And so you get the g composed with f of x is just 5 times the absolute value of x plus 1. And you're stuck with it in that form. All right, so that one's not too bad. All right, let's look at problem number 16. Number 16 is going to be messier algebraically. And I wanted to work through one messy algebraic problem with composition. And let's see. So I've got f is 1 over x minus 6, and g is 7 over x plus 6, like this. Now those are both have got rational functions. They both have fractions in there. And we've talked about the fact that when you have a fraction, that the denominator can't be 0. So the domain on the first one is that x can't be 6, right? Because you can't get a 0 in the denominator. So 6 is a restriction for f. And for g, 0 is a restriction, right? You can't have x equals 0 because that gives you 0 in the denominator. So this function, those restrictions would carry over to the final result at the end of the problem. That's a little bit about the domains here that I want to kind of point out. All right, so let's look at f circle g, f composed with g of x. So this is f of g of x. This one's going to be more complicated. This is going to be f of, in place of g, I put 7 over x plus 6. And now I go to my f function, right? Here's the f function. In every place I see an x, I could put an open set of parentheses. There's my f function, 1 over x minus 6. But in place of x, I put 7 over x plus 6. Now it looks kind of yucky here. That's really not that bad as it turns out, because this is 7 over x plus 6 minus 6. The parentheses really aren't necessary at that point. And so notice you just end up with 1 over 7 over x, like that. And that's just 1 divided by 7 over x. You invert and multiply, you end up with x over 7. You just flipped it, right? It's really 1 divided by 7 over x. So that's really 1 times x over 7. And so you end up with x over 7 as your final result. Now that function doesn't look like it has any restrictions on it, does it? But the function that you started with here, the starting function was g, and so the restriction on g has to carry over here. And so x cannot be equal to 0 in this problem, right? Because that's a restriction that carries over from the function g, and g was the starting function. So x cannot be equal to 0 here. No way that would be possible. All right? And so I wanted to make sure that we talked about that a little bit. All right, so the other composition in this case would be G circle F of X. This is going to kind of finish up composition, and we're going to start moving into inverses on the next example. So G circle F of X would be equal to G of F of X. And so this would be G of 1 over x minus 6, right? In place of the f, we put 1 over x minus 6. And now this says go to the g function. In every place I see an x, I put, this set of parentheses. So here's my g function, 7 over x plus 6. But in place of the x, I put an open set of parentheses. And then in place of the parentheses, or inside the parentheses, in place of the x, I put 1 over x minus 6, like that. All right, so that first fraction there, let's look at a little bit of scratch work here. That 7 over 1 over x minus 6 is really 7 divided by 1 over x minus 6. And you invert and multiply, so that's really 7 times x minus 6 over 1. And so that's what that first fraction, that ugly complex fraction, that's really what it's equal to, 7 times x minus 6, like that. And then that would be plus 6. And so this would give you 7x minus 42 plus 6, or 7x minus 36. And that would be the composition here. That would be G composed with F of x. It would be 7x minus 36. That does not look like it has any restrictions on it either, because it's just a linear function. But the beginning function in this problem was f, right? That was the function that started out. And f has the restriction that x can't be 6. And so that restriction has to carry over on this domain here, is that x can't be 6 in this function, because it depended on the domain of f, and x can't be 6 for f. So I'm not going to make a huge big deal about the domains. I just want to make sure you have some kind of basic understanding that the function that starts out here, in this case, when I say the function that starts out, that's this inside function here, that the restriction on that has to carry over to the end of the problem. And so the fact that f had a restriction on it, that x could not be 6 at the beginning, has to carry over at the end of this problem here. Okay. Now, the next problem I want to look at appears to be just another example of of composition, but this one in particular has got something that we want to talk about very specifically. So this actually goes to problems number 80 and 82, and you've got the functions f of x is x cubed plus 1, and g of x is the cube root of x minus 1. All right, so when you look at the composition here, so let's say we have f circle g of x, or f composed with g of x. So this would be f of g. And so the function that operates on x first is g, right? So this would be f of the cube root of x minus 1. And so this says go to the function f in every place you see an x. Right, we're going to put our set of parentheses there in its place. We drop in the cube root of x minus 1 in its place, like that. And so the cube root of x minus 1 cubed, well, when you cube a cube root, right, it's like those are processes that are undoing each other. And so you end up with x minus 1 there. So you end up with x minus 1 plus 1. And this is interesting. You just end up with x. And so you get that f circle g of x, or f composed with g of x, which is the same thing as f of g of x, is just equal to x in this problem. Now I want to look at the picture that you end up with here on this particular problem, that we've been talking about, right? We start off with x, and the function that operates on x first is g. And so g takes x to g of x, but g of x is equal to the cube root of x minus 1. So this is the cube root of x minus 1 right here. And then f takes over after that, and f takes the cube root of x minus 1. But notice what your answer is when f takes over. Your answer here is x. And so notice that f actually takes the cube root of x minus 1, and it actually takes it back to x right here. Look at the picture, right? The g takes x to the cube root of x minus 1, but f takes the cube root of x minus 1, and it takes it actually back to x in this problem. And so if you look at the picture, what you get here is that g and f kind of do opposite things, right? Here, g takes one value to the other, f goes in the opposite direction. Numerically, you could look at it with specific values. If you think of an x value here, and I'm just picking an x value out of thin air here, but let's pick something where the arithmetic at least turns out nice. So let's look at g of 9 as an example. G of 9 in our problem would be the cube root of 9 minus 1, right? Which would be the cube root of 8, which would be 2. So g of 9 is equal to 2. Now look at f of 2. F of 2 is equal to 2 cubed plus 1, or 8 plus 1, or 9. And so f of 2 is equal to 9. And so notice what you have here is that g of 9 is equal to 2, and f of 2 is equal to 9. That f and g switch or interchange x and y values. They do exactly the opposite. G takes 9 to 2, f takes 2 to 9. And that's exactly what that picture is saying right there. What happens here in a situation like this is that two functions where f circle g of x, or f of g of x, is equal to x, and g circle f of x, which is equal to g of f of x, is also equal to x. Now, we didn't show that on the functions at the top of the screen here, but it ends up that this will be true, that in both directions you get x as the answer. Two functions where when you compose them, either direction you compose them, you get x as an answer, then that means that this picture right here is describing what's going on in the problem. And we say that f and g are inverses of each other. Then f and g are called inverse functions. They are inverses of each other. Right? Two functions where the compositions give you x. In other words, two functions that interchange x and y values are going to be called, are what we call inverse functions. All right, so this, at the top of the screen here, when I've got f and g are called inverses, right? And what can we see right away here from what we've got in our function notation here is that the x values and the y values interchange. Notice I got a double-ended arrow there, is that the x value becomes the y value and the y value becomes the x value. They interchange x and y values, right? They switch x and y values. You could actually say it that way, that they switch x and y values. All right, two functions that are inverses are going to interchange x and y's. And the definition to prove f and g are inverses of each other, there's a way to prove it. You must show that f composed with g of x is equal to x and g composed with f of x is equal to x. On your next exam, in exam 3, I will ask you that. I will give you two functions and say, are these inverses of each other, right? And this is how you would show that they're inverses of each other, is you'd look at the compositions and see if you actually get x as an answer at the end, right? If you get x as the answer, then yes, those are inverses of each other. All right, so let's look at this problem right here. So show that f of x equals negative 3x plus 5 and g of x equals x minus 5 over negative 3 are inverses. This would be a very typical kind of question that I would ask you on an exam. I'd actually say use composition to show that f and g are inverses, right? And so the way you do this is you'd look at the two composition functions. You look at f composed with g of x. So that would be f of g of x. And you'd calculate this and see that you get x as the answer. So this would be f of x minus 5 over negative 3. And this would say go to the function f, and every place you see an x, you're going to drop that expression in its place. So there's my function f. Remember, f of x, let me write it right above it, is negative 3x plus 5. So in place of x, I put x minus 5 over negative 3. In other words, I dropped the g function into the f function. And then notice what happens there is that the negative 3's divide out, and you get x minus 5 plus 5. Or sure enough, you just get x. And so what have you got here? That f circle g of x is equal to x. Right? So you've got one of them shown. And so that's the start. That's halfway through the problem. You also have to show it the other way. Is it possible that one of the compositions gives you x, but the other one's not? Yes, it is. You got to kind of have to go out of your way to show it, but to have a function like that. But it is possible. So you do have to show both compositions. All right. So g composed with f of x would be g of f of x, like so. And so that would be g of, let's see, f of x is negative 3x plus 5. So in place of f of x, I put negative 3x plus 5. And then I'd go to the function g, and wherever I see an x, right, I put negative 3x plus 5. So open set of parentheses, minus 5 over negative 3. And in place of those parentheses, I put negative 3x plus 5. Don't forget that g of x is x minus 5 over negative 3. Like that. So what do you get there? Well, in the numerator, the parentheses really aren't necessary. And so you get just negative 3x plus 5 minus 5. The 5's go away, right? They add to give 0, and you get negative 3x over negative 3. And sure enough, you get x, because the negative 3's would divide out there. And so what did we just show? The g composed with f of x is got to be equal to x also. So what has got to be true here? F and G have got to be inverses of each other. No question about it, because both compositions give you x when you look at it. What does that mean? That one thing this means is that they switch x and y values. So when you switch x and y values, so for example, if I looked at, and I'm just picking something out of thin air here, if I look at f of 2 in this function, well, f of 2 would be negative 3 times 2 plus 5, because f of x is negative 3x plus 5. And so that would be negative 6 plus 5, or negative 1. Now look at g of negative 1. G of negative 1 would be negative 1 minus 5 divided by negative 3. So that'd be negative 6 divided by negative 3, or 2. And so notice that the point 2, negative 1 is on the graph of f. So this is on f right here. But the point negative 1, 2 is on the graph of g. What did they do? They switched x and y values. They interchanged the x and y values for these functions. All right, so if you looked at the graphs of functions like these, right? By the way, some notation here. Let me mention some notation. So f of x, which was equal to negative 3x plus 5, and g of x, which was x minus 5 over negative 3, are inverses. And so the notation we usually use with inverses goes like this. That we write f of x is negative 3x plus 5, and instead of just naming the other function g, we use this notation for the inverse. And that notation right there is read f inverse. You read that. You don't read it f to the negative 1. That is not an exponent. You read this f inverse. Right? When you see that notation like that. And that means you're talking about the inverse of the function f. So when somebody uses that notation, they're telling you that these two functions are inverses and that they switched their x and y values. And that if you compose them, you get x at the end. It is not an exponent. Make sure that you know that it is not an exponent. That is strictly notation. So it's not an exponent of negative 1. It's just notation. And it is read f inverse. And you read it f inverse when you see it. And you only use that notation when you know that you're talking about the two functions that are inverses of each other. All right, so if we have as an example here, we have f of x is the, let's say we have 2x cubed minus 1. Then the inverse of this function, f inverse here, f inverse, and I tell you what, let's just use, okay, so 2x cubed minus 1 is fine. We'll just write it that way. The f inverse is the cube root of x plus 1 over 2, like that. And it took me a second to make sure I wrote it down correctly. So that would be the cube root of x plus 1 over 2. Those two functions are inverses. Now, to prove it, you'd have to show that the inverses, that the compositions gave you x. You could get a good idea that you were right here. This doesn't prove it, but it does give you a good idea that you're right by just looking at some values here. So like look at f of 2. And what are you doing? You're looking at the values to see if they switch around. So f of 2 is 2 times 2 cubed minus 1. So that's 2 times 8 minus 1, which is 16, minus 1 is 15. So f of 2 is equal to 15. So now look at f inverse of 15. F inverse of 15 better be equal to 2, right? They better switch. And so you get the cube root of 15 plus 1 over 2. That's 16 over 1 over 2, which is, or 16 over 2, which is 8. The cube root of 8 is 2. And so you do get 2 there. That does not prove it. This does not prove these are inverses, but it does give you a good idea that you're right. Right? To prove, what would you have to do again? You'd have to use composition. So to prove, show, which we're not going to do here, but show that f composed with f inverse of x is equal to x. And what else? That f inverse composed with f of x is equal to x, right? You got to show both of those. Let me make my x's a little bit neater there. X and x. Okay, that's much better. You'd have to show that you'd get x in both cases there. All right, now some things about graphs here that we want to talk about. So let's look at a simpler cube root graph. Let's look at f of x equals, let's say we have x cubed minus 1, and its inverse, f inverse here, would be the cube root of x plus 1. Now we're going to talk about how I can write those down in a few minutes, and how we can actually find that inverse function in a few minutes. But right now I want to talk about the graphs. All right, these are inverses of each other. And so they are going to switch x and y values. And I'm going to hand draw these graphs here rather than going to an app or something. So the cube root of x minus 1, we've talked about, or I'm sorry, the x cubed minus 1, rather. I'm sorry, the x cubed minus 1. That's just the cube graph shifted down 1 unit. We've talked about the cube graph before. Remember, the cube graph has this shape. And so this is just shifted down 1 unit. And you could plot points here if you wanted to, certainly. And you get that the cube root graph kind of looks like this. Goes through those 3 points right there. If you wanted to look at more points, you certainly could. You know, 2, 7 is on the graph there. So 2, 7 is way up here. Right, there's a 2, 7 way up there. And then negative 2 would be negative 9. If you wanted to go down there, you could certainly do that. Way the heck down here. Right, that's negative 2, negative 9. So these are the points on our cube graph, like this. And remember, the cube graph has this kind of little pitch in the graph right there, and then it gets pretty steep pretty quickly. Like that. And so not quite as straight probably as I've just, I'm going to back up here a little bit, a little tiny bit. Okay, that's better like that. All right, so there's our cube root graph, or I'm sorry, our cube graph. I'll say it right eventually. Still don't like exactly the way it looks. Kind of picky about this. Okay, maybe a little bit better. So now the cube root graph, the cube root of x plus 1, we could just simply take these points that I've got here, and we could literally just switch the x and y values. We could plot points too, but if we just switch the x and y values, we will get the graph. So when I say switch the x and y values, you know, the cube graph goes through 0, negative 1, and so the cube root graph would go through negative 1, 0. Notice I just switched the x and y values. Our cube graph goes through 1, 0. So the cube root graph would go through 0, 1. 0, 1 would be right there. And then let's see, on the cube graph, we've got negative 1, negative 2. So our graph would go through negative 2, negative 1. And let's see, we've got -9, -2. So our graph will go through -2, -9 is on the cube graph. So -9, -2 would be on the cube root graph. So -9, -2, way the heck over here. And that would be at -9, -2. And we could do 2, 7 also. And I think that kind of is just barely on the screen there. So 7, 2, 1, 2, 3, 4, 5, 6. It's way over here, like that. So this graph ends up looking like this. And there's our cube root graph. That's the inverse function like that. And what happens here is, and again, let me kind of erase a little bit of this to show a little bit more. The bend's a little bit more pronounced than I had. There you go. That's much better. And what happens is, if you look at those two graphs, there is a certain amount of symmetry involved there. In fact, these two graphs are symmetric around this line that goes through the origin where the x and y values are equal. There's actually symmetry about that line. That line has equation y equals x, and this is actually always true, that the graphs of f and f inverse are always symmetric about the line y equals x. So if you can draw the line y equals x and you draw the two functions that are inverses of each other, you will always have symmetry around this line. So this is the function f right here, and this is the function f inverse right here. That will always be true, that they'll have symmetry about that line. Okay, so that's actually a good thing to know, because that is helpful when you're sketching graphs like this. All right. So if you have a function, let's look at a graph of a function right here. Not an equation at all. Let's just look at some graph. Let's say we have a graph that looks like this. And it goes through those 3 points. So let's see, that's -3, -3 right there. This point is at -2, 0. And this point is at 4, 2. Let's say we have a function that looks like that. And let's go ahead and extend those lines. That's okay. So let's say we've got the function continuing to look like this and goes on forever like that. And so this is our graph of f. So to sketch f inverse, given the graph of f, simply interchange all x's and y's. So in other words, at the point 4, 2, instead of the point 4, 2 on our inverse graph, we have the point 2, 4 right here. And instead of the point -2, 0, we have 0, -2 right here. And notice -3, -3, when you interchange there, you get the same graph, the same point. And so this graph looks like this. And remember, what should happen is you better have symmetry about the line y equals x also. Right, there's our graph of f inverse right there. And notice if I put in this line y equals x, this 45-degree line, where the x and y values are equal, notice I do have symmetry around that line with those two graphs like that. All right, so that's helpful to know. Now, a couple of things to mention here to finish this out about inverses that we need to discuss. First of all, some things about graphs that we need to discuss. Notice that if we take this function right here and do the same thing we just did above. Now this function should look familiar. This is actually the square function. If we take the square function like that and we interchange, let's say that this is f, like this. If we interchange the x and y values in this case, I want you to see that this is what's going to happen. So when you interchange the x and y values, you get this graph, and this is okay, but there is a problem here. That's the graph of the inverse. The graph of the inverse, though, fails the vertical line test. Fails VLT, remember that's the vertical line test. And so is not a function. Now we want to, when we talk about inverses, we want to limit ourselves to functions that whose inverses are functions, right? So notice in the first picture here, the two functions were both passed the vertical line test here. So both are functions in this case. So since they're both functions, the original function, the reason why its inverse was a function is that the difference between the first one and the second one is that on the first one, this graph f passed what we call, passes the horizontal line test. In other words, if you draw a horizontal lines only intersect that graph in one place. So it passes what we call the horizontal line test. We've never talked about the horizontal line test before. The second graph fails the horizontal line test. Right? Because if you draw a horizontal line, you can intersect it twice. So graphs that pass the horizontal line test are called one-to-one functions, and their inverses are functions. Their inverses are functions. Inverses are functions. All right, and so let's see. I want to kind of put a little box around that, sort of. Right, the original function passed the horizontal line test. That means it is what we call a one-to-one function. And so it means its inverse is going to be a function. A function that fails the horizontal line test is not one-to-one. And so its inverse is not a function. Right, so graphs that fail the horizontal line test are not one-to-one, and so their inverses are not functions. Now, what you sometimes will do to a function that's not one-to-one, a function that fails the horizontal line test, is you try to turn it into a one-to-one function by limiting the domain of the function. So this function is not one-to-one. So what we do is we limit the domain. So we restrict the domain. So we restrict the domain so it is one-to-one. In other words, it passes the horizontal line test. And so what we would do on this original function, I'm going to put it right next door to it here, is we actually restrict the domain to just x values greater than 0. And in other words, all we're doing, and don't make it too crazy, all we're doing is we're eliminating part of the graph and only looking at that part of the graph. Right? So we take a function that's not one-to-one, it fails the horizontal line test, and we restrict the domain. In other words, we erase part of the graph. That's really what you're doing, is you're just erasing. I'm just going to write this, put this in very, very lightly here. We're actually erasing that part of the graph that I put as a dashed line there. And what you have left is one-to-one. And then all of a sudden, its inverse is going to be a function. Right? It's going to pass the vertical line test and the horizontal line test. So here's our original function right here, is just half, quote unquote, half of the square function. And then the inverse function would just be the upper half of it, like this. And see now, so this would be the graph of f right here, and then the graph of f inverse would be this other one in green right here. And they do have symmetry around the line y equals x, notice. Right, if we can draw this line in here, right, we do have symmetry around that line, and then both of them are actually past the vertical line test. So these are both functions. Both are functions. So on a test, what I will ask you in particular is to be able to graph the inverse of a function given a graph, but then also to be able to tell when a graph represents a one-to-one function and when it doesn't represent a one-to-one function. Right? I just want you to know that one-to-one means pass the horizontal line test, passes the horizontal line test, and not one-to-one fails the horizontal line test. And passing the horizontal line test means that the inverse is a function here. It means we talk about the inverse. Inverse is a function. And here this means inverse is not a function. For those of you who are going to go on and take trigonometry, if you're some type of science major, this is going to be important to you as a trigonometry student, definitely. Because your calculator obeys these kinds of restrictions. So, all right, we have one last thing to talk about, and then we will be done. How do you create f inverse given f? All right, so what we're going to do is we are going to start with this function, f of x equals 4x cubed minus 5. And what I want to do is I want to find f inverse. So the last thing we need to talk about with inverses, and we'll be finished. All right, so to find f inverse, what you're going to do here is you're first going to rewrite the function. Instead of with function notation, you're going to replace f of x with y. So just replace f of x with y. And then you do what inverses do. Inverses switch x and y values. So you literally interchange x and y values. You interchange x and y. Because that's what inverses do. And that's the inverse. The only problem is it's not in a nice function form. So now you solve for y. So you take this and you solve for y. So you get y, you get x plus 5 equals 4y cubed. You divide by 4, you get x plus 5 over 4 equals y cubed. And then you take the cube root of both sides to solve for y, and you get the cube root of x plus 5 over 4 equals y. And that's what I did in those steps right there, is I solved for y. And then you finally, at the end, you replace y with the notation f inverse. So you get f inverse x equals the cube root of x plus 5 over 4. And you've created the inverse function, right? This function right here is the original function. It is a one-to-one function, so it would pass the horizontal line test. And so its inverse is also going to be a function, and here it is right here. We could graph it. You could look at the composition to prove that they're inverses of each other. You know, you could do all those different things we've been talking about here to kind of fit all this together. So, all right, so that's our that finishes our discussion on inverse functions. Rather than giving you any textbook problems for practice, I'm not going to even think about that. What I want you to do is I want you to work on exam 2 review this week. So this week, what do? You finish WebAssign homework. You've got till tomorrow to look at 5.5 and 5.6, which is on the exam, so that's reviewing for the exam. And then work on the exam 2 review. And then remember, the exam 2 is taken from March 22nd through March 27th. Please email me, send me a WebAssign message, send me a remind message. You've got lots of ways of getting in touch with me. I can certainly try to make an appointment with you sometime to meet with you to kind of go over some homework problems if you need me to. Friday and Saturday of this week, I will not be available for any type of appointments, and I will not be reading email, so no emails will be read. This would be on March the 23rd or 24th. I will be out of pocket and will not have access to a computer, will not have access to the internet for those 2 days. And so, so you can email me those days, but I won't be responding until the 25th when I get back. And I will be on the 25th, we'll be online 8:30 to 9:30 at night also. Okay, so just wanted to mention that also. All right, so everybody have a great week. Hopefully you work hard going into exam 2, and let me know if you need any help. I'll be happy to help you out. Remember, I'll be on campus on Wednesday and Thursday of this week.